All right, as an extension, since we have the equation for f of x, let's see what happens when we actually graph the function g of x, the thing that I was calling a rational function. So remember that at the very, very beginning, we talked about g of x being the quotient, the ratio of f of x over x plus 3. This is the definition of a rational function, assuming that these things are polynomials, which they are. So since we went through all the trouble of finding what the equation of f of x is, let's see what g of x actually looks like. So g of x was supposed to be f of x divided by x plus 3. Okay, we found that f of x essentially is this guy here. So f of x is equal to this 4x plus 36. So now I'm going to write g of x is equal to 4x plus 36 over x plus 3. Now, rational functions, a ratio, implies division. That's what this bar is right here. So basically, it's taking the graph of 4x plus 36, y equals 4x plus 36, and dividing it, y value by y value, with x plus 3, or x plus 3 is being divided into that. Here, let's see how that plays out on Desmos. So I'm going to go over here to this next line, and I'm going to type in the bottom here as a function, so y is equal to x plus 3. And this is some weird business here, so let me, okay, this is a little bit better. Okay, and I don't like the color of this graph. Let's have a, ooh, how about, yeah, about orange. Ooh, blue and orange, that looks good. Okay, so essentially what we're doing is that we are taking y value by y value and dividing these two things here. Let me just kind of demonstrate this with, I don't know, x is equal to 1, and then it should put a little slider in here for me, right? Okay, so for example, if I put my vertical line here, it's taking these two y values here, in this case 10.8, the y value for the top one, and dividing it by the bottom y value, which is negative 3.3. It's doing that for every single y value. Okay, so let's see what this thing looks like whenever I actually graph it. So I can get rid of this. Let's graph g of x. G of x is equal to, and then I'll go ahead and throw the division. Makes it a little bit easier for me to format. I don't have to worry about like parentheses. So 4x plus 36, there we go. And on the bottom, x plus 3. Okay, this is a strange graph here. Let's hide these things temporarily. And what is the, oh, that's this linear regression that's there. Okay, so here is the graph in question, and I will show you something pretty spectacular, and that is this. Let's hide these points, and let's show the y1 original points, and then let's see, can we zoom so we can see these points? Right, so notice that all three of the points they gave us are perfectly on this, this graph, this rational function here. And now also notice this, let me zoom a little bit more. Notice that the graph is kind of broken here. It's broken vertically and it's broken horizontally, as if it doesn't cross a couple of lines. And we call those things asymptotes, which you may remember from Algebra 1. Usually you talk about asymptotes with exponential functions as a line. Your graph gets closer and closer and closer too, but ultimately doesn't get there. Well, it does at infinity. Anyway, so here, let's look at, well, remember if I put this thing back in there, this little, this is the denominator there, the orange graph, where it is equal to 0, that's x is equal to negative 3 here. At the very beginning of this, I explained that we couldn't divide by 0, and if I plug a negative 3 into this graph, x on the bottom as negative 3, I just divided by 0. So watch what happens if I just graph x is equal to negative 3. And then what we like to do here is format this like so as a dashed line, as it's not part of our actual graph, but it is that vertical asymptote that this This rational function is trying to get closer and closer to. Notice that that is the same exact y value of my denominator. Let me hide this thing back again. And then if I zoom out, you'll see that our graph of the purple one, which is the rational function, is getting closer and closer and closer to it. And again, this is what's happening if you divide by zero. It's like you just created yourself a black hole on your graph. Okay, but there's another asymptote, and that is a horizontal one. So it looks like right here at y is equal to 4, y is equal to 4, that seems to be something that the purple graph is getting closer and closer to. So let me type this one in. So y is equal to 4. And I'll do the same treatment that I did on the last one to make this thing a little dash graph. There we go. Yes, so you can see that that is in fact the case here. Okay, right, and there is something about the original graph which would suggest the y is equal to 4 in the same way that the vertical asymptote was suggested by the equation there with the denominator. See if you can figure that out. Okay, one small extra feature of this is, in fact, this point here. So we already talked about this one, the -3 comma 0, basically coming from where the denominator is equal to 0. Okay, whoops, I don't want to hide this one. How about this x-intercept for the original graph here, the what is this thing called? Rational function, yes. So this -9, 0. Where did this one come from? Here, let me show you. Let me put the top of this on here, and then you'll see that that's exactly where the top function, the one that we spent so much time trying to find, y is equal to 4x plus 36, that's the x-intercept for that graph. Okay, and then there's one other thing here. So let me go back here so I can write. Let's assume that we plug in 0 for each one of these. If I plug in 0 for my x, so basically finding g of 0, when your x value is 0, that's the y-intercept. So I would have 4 times 0 plus 36 over 0 plus 3. These guys just go away because we are zeroing them out. And I just essentially have 36 divided by 3, which is 12. In other words, the point 0, comma 12. Not that our SAT question had anything to do with this, but this is just another little feature of this. If I were to type in 0, comma 12, that is where this purple graph should touch the y-axis, and in fact, that is exactly correct. Now, one last thing about these asymptotes. Will this purple graph ever cross that vertical dashed line, the asymptote? And the answer to that question is no, because if it did, you would be dividing by 0, this thing right here, which is not something that we tend to do. And another question is, will the purple graph cross the horizontal asymptote? In this case, it does not, because our function g of x is never equal to y is equal to 4. I can show you that really quickly. For example, if I wanted to see if this graph was ever equal to y is equal to 4, I just set it equal to 4. So 4 is equal to 4x plus 36 over x plus 3. And then I can multiply this thing over to the other side, and I have 4 parentheses, x plus 3, 4x plus 36. Distribute this 4 on the left-hand side. 4x plus 12 is equal to 4x plus 36. I could subtract 4 x's from both sides, and I'm left with the nonsense that 12 is equal to 36. This implies that the only way that our function can equal 4 is if 12 is equal to 12 is equal to 36, which is not. So it's never, ever going to cross that line. There are some rational functions that you will see next year in Algebra 2, which it will. Okay, so that's probably a deep enough dive into these rational functions and the equal asymptotes and things that happen when you divide two functions together.